Let's have a look now at exponents, roots, and how they pertain to the order of operations. Whenever we have an exponent, what we're talking about is repeated multiplication. So, for example, 3 raised to the second power. This number here is called the base, while this number is called either the exponent or sometimes called the power. And whenever you take a base and raise it to a power, what you're doing is you're taking that base, writing it that many times, and then multiplying. So the 3 gets written twice, and you multiply to give you 9. And all the rules of multiplication are as usual. You multiply fractions the way you normally multiply fractions. You multiply decimals the way you normally multiply decimals. All the rules of multiplication are still the same. The exponent merely tells you how many times you're multiplying. Keep in mind that changing the order of these does change the result. 3 to the second power is 3 times 3. 2 to the third power, you would take, again, your base and write it that many times. So you would write the number 2 3 times, and then multiply those together. 2 times 2 is 4, times 2 more is 8. Okay? Keep in mind that this works for any number. It doesn't have to be a rational. It doesn't have to be an integer. It can be any number, rational or irrational. So, for example, we can have a fraction, let's say 3/8, and we can raise that 3/8 to the second power. And again, that means take 3/8 times another 3/8. And again, the rules of multiplication happen as usual. 3 times 3 would be 9. 8 times 8 would be 64. Okay? And with a decimal, again, the same thing would happen. Let's say we had 0.4 raised to the third power. Well, that would be 0.4 times 0.4 times 0.4. Okay? Here, we're going to multiply these one pair at a time. So let's start with just these two. 0.4 times 0.4. I'll do this to the side. Well, 4 times 4 is 16. Now, this decimal is one space from the end, and this decimal is one space from the end. So together, in your answer, you have a decimal that is 2 spaces from the end. So that would be 0.16. So here that would be 0.16, the product of these two. But now you still have to multiply that times another 0.4. Okay, so we can take 0.16 times 0.4. 6 times 4 is 24. We carry our 2. 4 plus 2 more is 6. And here, our decimal is 1, 2, 3 spaces from the end. So from the end, 1, 2, 3 spaces. Notice there's a blank there. We're going to fill that in with a 0. So that's going to give us 0.064. Like that. This is in the tenths place, the hundredths place, and the thousandths place. So this would be read as 64 thousandths because that's the last number. Right? Here, same thing. This would be 16 hundredths because tenths, hundredths, and this would be in the tenths place. So this would be 4 tenths. Right? Most people find it simpler to just say point and then repeat the number. However, you will sometimes run into the more formal expression of stating it by place value. Once again, tenths, tenth hundredths, tenth hundredths, thousandths. So this would be 64 thousandths. This would be 16 hundredths, and this would be 4 tenths. So just keep that in mind. You'll occasionally run into that language. Speaking of language, usually when we talk about an exponent, we refer to it as a power. So for example, something like 3, like this could be read as 3 to the second power. Something like this would be read as 3 to the third power, 3 to the fourth power, 5th, 6th, and so forth and so on, like that. So you would read this as first, there is a first power. Now, of course, the first power doesn't do anything because you're just saying 3 times itself one time. Well, that's just the number 3. So here that would be 3 to the first power. 3 to the 5th power, and so forth and so on. These two have a different name. You can say second and third power, just like we have here. However, an alternate, often used phrase for the second power is to say squared. 3 squared. And the third power is often referred to as cubed. So instead of saying 3 to the third power, it's common to say cubed. Right? It's just an alternate labeling for these two. Here, first power, fourth power, fifth power, sixth power, you just read it as whatever the power. But for the second power, it's often referred to as squared, and for the third power, it's often referred to as cubed. You can use either one of these, and they are interchangeable. Now, whenever you see an operation, you often have its counterpart, one that undoes it. So, for example, addition and subtraction, they undo each other. If I have a number and I add 5, and then I subtract 5, well, it's as if nothing happened. If I have a number and I multiply by 3 and then divide by 3, it's as if nothing happened. Addition and subtraction undo each other. Same with multiplication and division. Well, this is an operation. An exponent, a power, is an operation. So what is its counterpart? Well, those are called roots. This is the symbol for a root. Incidentally, just a quick historical note, this is actually the letter R. It kind of looks like the letter R, and in fact, that's what it is. If you read some historical documents in math, things used to be written in full. You would say something like the root of 5. And then eventually people got a little lazy and they said, okay, instead of writing out the root of 5, we'll just write root 5. And in fact, that's still commonly stated. You'll hear me say it, root 5, root 3, root 7. And then after a while, people got even lazier and said, well, we'll just write the letter R for root, so root 5. And then over time, that symbol, the letter R, became corrupted slightly, and it became the typical root symbol that we have now. Right? So here, this is read as a root. Say a root. Don't you mean the root? Well, just like there are different exponents, there are different roots. So this one is referred to as the square root. Second, square root. This one is going to be the one that undoes the square. But there's going to be others. There's going to be the cube root. And then there's the fourth root. And the fifth root, and so forth and so on. Okay. Whatever is in here, you might have just one number, or later on we'll have bigger expressions. Everything that's underneath this bar is being subjected to this operation. So in a way, it acts like parentheses. Anything in here is being held together. Whenever you deal with roots along with other operations, we're going to treat these as if they were parentheses. Anything underneath the root is considered a single expression all held together. We'll see that here in just a few minutes. If you are down to just the square root of a single number, then as the counterpart of the exponent, it's going to be dealt with at the same time as the exponents from left to right. And again, we'll see that here in just a moment. Now, although there are different roots, right now, we're only going to deal with the square root. All the other ones are similar in nature, but we're going to start with this. All right, so the square root is essentially asking you, what do you square to get what's in there? this number in here, and later on it might not be a number, it might be a variable expression, something a little bit bigger, but whatever's under here is called the radicand. So here we're taking the square root of this radicand, and when we take the radicand, what we're asking for is what number can we square to get that radicand? Oh, well, it seems like we can square the number 5. Well, yeah, but we could also square negative 5, couldn't we? After all, 5 times 5 is 25. But also negative 5 times negative 5 would also be positive 25. So how do I know which one to use? Whenever we have a square root, we automatically assume we want the positive one. If we want the negative one, we'll ask for it by actually writing a negative out in front. So here, that would be 5, whereas this one would be negative 5. Yes, it's true. There are 2 different roots of 25, because after all, you can square 5 to get 25, or you can square negative 5 to get 25. So in order to keep that from being ambiguous, and in order to keep us from wondering which one we want, the notation explicitly asks us for it. If there's a minus here, that means we want the negative one. If there's not a minus there, that means we want the positive one. So the notation will inform you which one it's asking for. So when you have a square root, the square root of some number x is asking what do we square to get x? Okay. The other roots would ask the same thing. The cube root asks, what do we cube to get the radicand? The fourth root asks, what do we raise to the 4th power to get the radicand, and so forth and so on. But again, we're going to stick with just the square root for now. Okay? So, for example, or further examples, after all, this was an example here. As a further set of examples, let's say we take the square root of 81. And again, what we're asking for is, since there's no minus in front, we want the positive one. What positive number can we square to get 81? Well, that would be 9 times 9 is 81. So the square root of 81 must be 9. Okay. Again, if we want the negative, we'll specifically ask for it. If we say negative root 36, now this is asking for what negative number can I square to get 36? Oh, that would be negative 6. Negative 6 times negative 6 is positive 36. Now this will work for a fraction as well. The nice thing about fractions when it comes to roots is that each part of the fraction, the numerator and the denominator, are handled separately. So for example, if I have 9 over 16 and I want to take the square root, I don't have to worry about it as a fraction. I can just look at the top and the bottom separately. Here, whenever you take the square root of a fraction, you can take the square root of the top, separately take the square root of the bottom, like that. So the square root of 9, what positive number can I take and square to give me 9? Well, that's going to be 3. And what positive number can I square to get 16? Oh, that's going to be 4. So the square root of 9/16 is 3/4. And of course, if you're not sure, you can always check this. If you square this, you should get your radicand again. If you square this, you should get your radicand. If you square this, you should get your radicand. Go ahead and give that a try. Simplify the following expressions by taking their roots. Let's have the square root of 121. Let's take the square root of 64 over 81. And then let's try negative square root of 1. Okay, go ahead and pause the video, and once you have a result, go ahead and unpause and we'll confirm those together. All right, the square root of 121 is saying, okay, I want a positive number, because there's no negative in here. I want a positive number who I can square to get 121. Well, that's going to be positive 11. 11 times 11 is 121. To take the square root of a fraction, I can handle the top and the bottom separately. The square root of 64, that's going to be 8, because 8 times 8 is 64. The square root of 81 is 9, because 9 times 9 is 81. And so I get 8 over 9 as my square root. Here, because of the negative, I want a negative answer. Okay, so it's going to be negative something. Negative square root of 1. What number can I square to get 1? Well, it's got to be 1. 1 times 1 is 1. So there we go. Note that because you're taking a square root by asking what do we square to get the radicand, it's useful to remember the list of squares. Now, the list of squares goes on forever, but remembering just the first few is often useful. Remember that 1 squared is equal to 1. Remember that 2 squared is equal to 4. 3 squared is equal to 9. 4 squared equals 16. 5 squared equals 25. 6 squared equals 36. 7 squared equals 49. 8 squared equals 64. 9 squared equals 81. 10 squared equals 100. 11 squared is 121. And 12 squared equals to 144. Now, obviously, we keep going, 13 squared, 14 squared, 15 squared, and so forth and so on. But at least these are useful enough because they appear very often. The smaller numbers appear more often. These numbers here, if you take their square root, are going to give you one of these whole numbers. The square root of 36 is 6. The square root of 144 is 12. If you have fractions that are made up of these numbers, then they're also going to have nice whole numbers as their numerators and denominators. Whenever you have a number like that, that is either the square of a whole number or the square of a rational number, that's called a perfect square. So definition, a perfect square is a number that is the square of a rational number. Now remember, rational numbers also include whole numbers, but they also include fractions and decimals that either terminate or repeat. All right? So for example, well, the examples that we already had were the squares of the whole numbers. So 5 squared equals 25. Okay, so 25 is a perfect square. But if I take a rational number that isn't a whole number, for example, 3/7, and I square that, that's going to give me 9 over 49. And again, that 9 over 49 is a perfect square because it's the square of a rational number. Remember that rational numbers can take the form of decimals so long as those decimals terminate or repeat. Repeating decimals we wouldn't want to square because, well, it would take literally forever to multiply all those numbers up. We'd want to leave that as a fraction. But if you had a terminating decimal, that would be simple enough to do. 2.5 squared is 2.5 times 2.5, which is 6.25. Okay. Oh, I forgot to carry my 1. 2 times 5 is 10. And then 4 plus 1 is 5. There we go. So 6.25. All of these are perfect squares. One thing to note is the square root of any number that is not a perfect square is irrational. So if I take the square root of 25, well, then I get the number 5. Okay. If I take the square root of 9 over 49, I get 3 over 7. And if I take the square root of 6.25, 6 and 25 hundredths, then I get 2.5. I get 2 and 5 tenths. But now let's say I take the square root of a number that is not a perfect square. Say, for example, I take the square root of 13. 13 is not a perfect square. It's not one of the numbers that you can get when you square a rational or a whole number. So because of that, this is an irrational number. You say, so what do we do? Generally nothing. An irrational number is a number that, when written as a decimal, will never terminate. So you'll never have a nice place you're going to stop. And it never repeats. So you can't just say something like 2.5555, forever. It will go on forever, unpredictably. We don't know what the next term is until we find it. We don't know what the next number is until we find it. So because of that, an irrational number, if we write it as a decimal, we're never really going to get a nice closed answer. So because of that, irrational numbers, we generally just leave them the way they are. If a number can be simplified, we simplify it. If you can actually take the square root of your radicand, then you do it to get a smaller, more convenient number. But if you cannot, well, then you just leave it like that. There's nothing wrong with leaving a number as a square root of 13, just like there's nothing wrong with leaving a number as a fraction and not turning it into a decimal. Or just like there's nothing wrong with having a number that's a decimal and not turning it into a fraction. It's just another way of writing it that is convenient for that particular instance. So this one, we're not going to bother with trying to convert this into a decimal. It's just, what's the square root of 13? That's what it is. It's the square root of 13. It's like saying, what is 3/7? Well, that's what it is. It's 3/7. That's the number. All right. So now let's talk about the order of operations. Remember, whenever you handle different operations within the same problem, addition, subtraction, multiplication, division, you're going to have an order in which you handle these operations. You're going to have parentheses. You're going to have exponents. You're going to have multiplication, division. And you're going to have addition, subtraction. Remember, when you're handling multiplication, division, you don't always have to do all the multiplications first. You don't always have to do all the divisions first. You do them in order from left to right. Likewise, addition, subtraction. It's not that you always do every addition before you do any subtractions. It's that you do addition and subtraction at the same time, going from left to right. Parentheses. Note that parentheses, they're called parentheses, but there are different delimiters. There are different symbols that help you group. These are actually called parentheses, but there are other ones which are similar, which behave similarly, but they have different names and a different shape here. These are called brackets, and these are called braces. And there's no difference between these in the functionality. There's no reason why you use one over the other. The reason why you have different shapes is mostly for aesthetics. If you have a bunch of parentheses in a problem, it gets really hard to tell, okay, this one pairs with that one, or this one pairs with that one. If you have a problem that looks like this, 2 minus open parentheses 3 plus open parentheses 5 minus 4 close parentheses plus 7 close parentheses minus 6. After you have enough parentheses, it kind of gets hard to tell, okay, wait, that one is with that one? No, that one's with, okay. It's hard to tell which one is with which. So when you have a lot of parentheses, it might be useful to have different shapes. That way it's easier to tell, oh yeah, look, that one's paired with that one. and then this one is paired with, I had made a mistake. When they were all the same shape, I actually messed that up. So there we go. So now it becomes a little more apparent. Oh yeah, these are paired together, and these are paired together, and these are paired together. Otherwise, there's no difference between these. Absolute values are a little different. Remember, they are going to act like parentheses in that anything inside of them is held together and done first. But then absolute values also have one extra action. They take the absolute value of the number inside. Also, a square root will behave like parentheses, meaning anything inside of here, if you have several different things in here, everything underneath the bar will be considered to be in parentheses. Even if the parentheses aren't written, they're considered to be there. Okay? So let's take a look at a problem that involves the order of operations. Let's say we're going to take 5 minus 3 times the square root. No, whenever you have 3 times something, or whenever you have a number multiplied by something in parentheses, and that includes any of these, we generally don't write the multiplication symbol here. You just write it next to it. So this is 3 times this square root. But if that makes you uncomfortable, you can write it. There's nothing wrong with writing it, but you'll often see it written just this way. Okay? So this is 5 minus 3 times the square root of, let's say, 6 squared plus, open parentheses, 5 plus 8. Like that. Plus 4. Oh, let me make that an 8. Plus 8 divided by 4 times 2. All right. So let's go ahead and do this problem. All right, parentheses come first. Notice that everything in this radical is held together with parentheses. Now, notice the parentheses aren't written, but they're understood to be there. Because all of this is underneath one radical. You can imagine, or if you prefer, you can even physically write these parentheses and say, okay, all of this is together. Okay, so that's going to go first. We're going to look inside of that radical, inside of that square root, and within that square root, we notice we have some operations. Within these red parentheses, I have a power, I have addition, and I have more addition inside of these parentheses. All right? So even within these parentheses, we still have to follow the order of operations. So out of these 3 operations, square, addition, and parentheses come first. All right, so the very first thing we're going to handle is we're going to do this addition. 5 plus 8 is 13. I'm going to write everything else exactly the way it was. You might notice I put a little hook on the end of that. That's just an old habit of mine. What it does is it makes it very, very clear. Here's where I've stopped. Because especially if you write very small, or if you're trying to write in a closed space, it makes it a little hard to tell, okay, wait, where did this end? Did it go here? Did it go up to the next number? The little hook makes it a little clear. Huh, I stopped right there. If you don't put the little hook, that's fine. It's just a habit of mine. It makes it easier for me to see. All right. So now within these parentheses, I still have 2 operations. You say, well, I don't see any parentheses. Well, remember, they're understood to be there. Again, if you want to draw them, you can, but they're not necessary. They're understood to be there. Here, I have an exponent and I have a sum. Well, again, even within these parentheses, I follow the order of operations, and exponents come before any addition or subtraction. So here I'm going to square this as my next step. 6 squared, 6 times 6, that's 36. And everything else has remained the same. Okay. Well, again, I still have parentheses because everything inside of the radicand is one expression. So that's the last operation still in those parentheses, so let's complete that. 36 plus 13 is 49. All right. Okay, so now let's continue. Notice this has been condensed down to a single number. It's just 49. But since it's inside of a radical, we're still not really done with this because this is still going first. We're going to take the square root. Okay, so now let's take the square root of 49, and that's just the number 7. So that's 5 minus 3 times 7. And here, let me actually write the times symbol there. Times 7 plus 8 divided by 4 times 2. Like that. All right, so now all my parentheses are done because I've condensed this down to a single number and taken its square root. All right, so now next we want to look at exponents. Okay, well, I notice there's no exponents in here. All right, well, there's no exponents. Let's move on. Next, we do multiplication and division. Notice this doesn't mean do multiplication first. It doesn't mean do every multiplication first before you do any divisions. What it means is do multiplication and division in whatever order they appear in from left to right. If I go from left to right, first thing I notice is this multiplication. Okay, so I'm going to do this first. That's 5 minus 3 times 7 is 21. Okay. All right, now I continue. The next one that I see is this division. Notice I didn't do all the multiplications first. I did that one first because it was the first one to show up. But now this is the next operation that shows up, this division. So let me do my division. 8 divided by 4. So 5 minus 21 plus 8 divided by 4 is the number 2. And that's still being multiplied by 2. Now I have one last multiplication division. In this case, it's a multiplication. Since it's the last one that appears, it's the last one that I do. 5 minus 21 plus 4. And finally, I have two operations left. I have addition, subtraction, and here I'm going to do them from left to right. So the first one that I see, 5 minus 21, it's going to be negative 16. Remember, subtracting numbers is the same as adding its opposite. So this is the same as saying 5 plus a negative 21. 5 plus a negative 21. Adding two numbers that have opposite signs, you're really subtracting them. So 21 minus 5 is 16. And then you're going to keep the sign of the number that has the greatest absolute value, which is this one here. So you're going to keep your negative. So 5 minus 21 is negative 16. And finally to that, you're going to add the number 4. Once again, you are adding two numbers that have opposite signs. So really you're going to subtract 16 minus 4. That's going to give us 12. And then we're going to keep the sign of the number that has the biggest absolute value, which for this is the negative. So there we go. This condenses down to negative 12. All right, so go ahead and give this a try. Okay, let's see here. So let's take 4 plus the square root of 21 divided by 7 times 3 plus 4 squared minus 3 times 2 squared minus 3 to the third. Okay, go ahead and give that a try, following the order of operations. Notice here you have two groups of parentheses, this one and this one. Well, again, anytime you have things that are of the same category, you're just going to go from left to right. So whenever you have addition, subtractions, you just go from left to right. Multiplications, division, you go from left to right. If you have several parentheses, you're going to do the same thing. You're going to go from left to right. So here, if you have several ones, go ahead and finish this one, then that one. So give that a try. Pause the video and simplify that down. And once you condense that down to just a single number, go ahead and unpause and we'll go through it and confirm together. All right, so let's go through this. Remember, all of the stuff underneath this radical can be thought of as being in parentheses. So we're going to do all this first. So let's ignore all the rest of this. Within those parentheses, we see division, multiplication, addition, and squaring. Okay, well, out of all of these, exponents go first. So this is our first operation. 4 plus the square root of 21 divided by 7 times 3 plus 16 minus 3 times open parentheses 2 squared minus 3 to the third. Okay, so now we've handled the exponent, but there's still other operations. I see division, I see multiplication, and I see addition. Okay, so multiplication, division happen first, and again, we handle them from left to right. So the first one I see is 21 divided by 7. Okay, that's going to give me 3. Times that 3 plus 16. And then I do the multiplication. 3 times 3 is 9. Now, we're still in these parentheses. We're going to do the addition. 9 plus 16, that'll give us 25. And finally, we're going to take that square root of 25, which is just the number 5. Okay. All right. We've handled one set of parentheses, but now we have to handle the others. We can't do anything outside until we do this. Within these parentheses, I see a squaring, a cubing, and a subtraction. Okay, well, exponents come before subtraction. So let's go ahead and do the exponents here. Left to right, 2 squared. We're going to do that first. So that's going to be 4 plus 5 minus 3 times. Here, 2 squared is 4. Minus 3 to the third. Remember, 2 squared means 2 times 2. 3 to the third would be 3 times 3 times 3. Minus 3 to the third is 3 times itself 3 times. So 3 times 3 is 9, times another 3 is 27. Okay. We're still within these parentheses, so now we need to subtract. 4 minus 27, that's the same as 4 plus a negative 27. If you have two numbers with opposite signs, you're subtracting them. 27 minus 4 is 23, but then we're going to keep the sign of the number with the biggest absolute value. And since that's the negative, that's going to stay a negative right there. Okay. So now I have addition, subtraction, and multiplication. Okay, well, multiplication is going to come first. So we're going to do this. A negative times a negative. When you multiply two numbers that have the same sign, you end up with a positive. So really that's going to become a plus, a positive. 3 times 23 is 69. And since that's a positive, this whole thing is now plus. So this is now 4 plus 5. This was minus something, but because you multiplied by a negative, that became a plus. And finally, you have only two operations left. They're both of the same category. You have nothing but addition left. So here you're going to go from left to right. 4 plus 5 is 9. Plus 69 is 78. And for some reason, I've been forgetting to write my equal sign all day today, haven't I? This is equal to that, that's equal to this, that's equal to that, all the way down until we get to our final result. So in the end, we condense this down to a 78. One thing to note is that these questions do not have to be asked symbolically. They could be asked in words. So for example, you might be asked, what is the product of 6 and the square root of 9. Okay. All right, so there's a few keywords here that tell us what operations we want. Product, that's multiplication. Anytime you see the word product, multiply, times, that's going to be the multiplication of two things. Okay. So whenever you see the word sum, more than, now notice that's not is more than, that would be an inequality. This is just the phrase more than. Addition or plus, that's going to be this symbol. This is difference. Less than. Now again, that's less than. Is less than. If you have the word is right here, that would be an inequality. Greater than, or is less than. Subtraction from, and minus. Those are all this symbol. If you see product, if you see times, or if you see multiplied, that's our multiplication symbol. And if you see the word quotient, if you see ratio, which is an old word that means the same as a fraction, or if you see into, like 10 goes into 55 times, into, that would be division. Also, this one's a lot more specialized. It doesn't happen very often, but there's also percent, because after all, percent is division, although it's a very specific division. Percent is division by 100, divided by 100. 20% is 20 over 100. Okay. And then for any powers, you would simply say the power to the whatever power, or in the case of squaring, cubed. To the blank power, where the blank is whatever power you need, to the first power, second power, third power, fourth power. You also have roots, and again, that's simply stated, square root of. Here we only really deal with square roots. We don't deal with any cube or fourth or fifth roots, but here you would simply say it that way. Instead of saying square root, you would say cube root, fourth root, fifth root of, like that. And with delimiters, parentheses, whether they be these parentheses or a different shape, you will often just simply hear open parenthesis, close parenthesis, where open parenthesis means you start your parentheses and close means you end it. Another word is quantity, which we'll see here in the next example. Here you might see open parentheses, close parentheses. Those would come together. Open parentheses would start it and close parentheses would end it. And you might see the word quantity. Okay, so here let's do some examples. What is the product of 6 and the square root of 9? Okay, well, product means, right here, you're multiplying. Okay, so what are you multiplying? The word and tells you the things that are being multiplied. 6 and square root of 9. Okay, so we're going to multiply two things. One of them is the number 6. The other one is the square root of 9. Well, again, square root of, that's going to have that symbol around the 9. And there we go. So now the order of operations, here we're going to handle the square root first, as if they were part of the parentheses. So this would be just the number 3. And here 6 times 3 would be 18. Just like that. Another example, you could say the quantity six less than 10 squared. Okay, the quantity 6 less than 10 squared. Okay, quantity means parentheses. Okay, so how does that work? When you say the quantity 6 less than 10 squared, that last word is what's being applied to the parentheses. Because without anything extra, if we didn't have that squared there, we wouldn't need that word. We would just say 6 less than 10, and that's it. It's subtraction. All right? Less than means subtraction. If we need parentheses, it's because something else is happening besides that one operation. Okay, well, what else is happening? Well, we're squaring something. Okay, so the quantity, 6 less than 10 squared. That extra word out there is this square is being applied to all of this stuff. So when we say the quantity, that means here's your open parenthesis, and then you're squaring. Okay, so then that means that's your closed parenthesis, and you're squaring on top of that. So the way this is going to look is, okay, in the parentheses, we have 6 less than 10. Okay, so you're going to start with 10, and then you're going to take away 6, right? Because you have 6 less than that. So you took away 6. 10 minus 6, that's 6 less than 10. And now that quantity, the whole thing is being squared. All right, so now the order of operations, parentheses go first. 10 minus 6 would be 4. And then that 4 is squared, which gives us 16. And that makes us happy. So keep that in mind. These words that are used to key you into what notation are we supposed to use, what operation are we supposed to use, these don't come up very much just yet. Right now we're simply learning the way in which real numbers work, the operations and how they're grouped together. This becomes a lot more prevalent when we start dealing with word problems. And I misspelled cubed. I put an extra E there. There we go, cubed. When we start dealing with word problems, applications, then you'll start seeing more phrases and mixed in with the operations here. So this isn't something that one learns all at once. This is something we'll keep seeing a little at a time until eventually we become familiar enough and comfortable enough with these types of phrases that they're just as meaningful as the symbols are. So that is it for this topic. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.